Hey everyone, welcome back to Calculus 3. This will be the 9th lecture of the course. In this section we're going to get into a very important application of vector valued functions specifically, but calculus in general. And that's going to be the modeling of velocity and acceleration. This would be obviously a huge application from the world of physics. Okay, so let's go ahead and jump into that. Okay, so we'll call this section 2.3, velocity and acceleration. Okay, so up to this point we have discussed a lot of things, obviously. We've discussed parametric equations. We've discussed curves, vectors, derivatives, obviously, and most recently, vector valued functions. Okay, and so what we're going to do is we're going to combine all of these ideas and basically crank out this huge application for physics. Okay, so velocity and acceleration. So let's get a little bit of kind of a little bit of background here. What are we talking about here? So as an object moves along a curve in the plane, okay, so imagine we're in the plane here. As an object moves along the curve in the plane, the x-coordinate and the y-coordinate of its, we'll just think of it as having a center of mass. Okay, the x-coordinate and y-coordinate of its center of mass can be considered functions of time, right? So we can think of this as xt and this as yt. And so wherever the function happens to be at time t equals t0, t naught, there's going to be some kind of a coordinatization of that. Okay. All right. And so if you kind of think of it in these terms, then we can use the vector valued function setup that we've just described to describe the position of the particle at any time t. All right. So we can have a position vector r of t, and it'll take the form in the two-dimensional plane of x of t times the I vector plus y of t times the j vector. Okay. All right, so you've got this position vector, you plug in some time t, and it tells you where in the two-dimensional plane the particle's center of mass happens to be. Now, the beauty of this approach is that these two quantities, velocity and acceleration, can be quickly derived from this position vector. Okay, so velocity is just going to be the derivative of the position vector, and acceleration is going to be the derivative of the velocity vector, and another way to say that is it's the second derivative of the position vector. Okay, so velocity, and hopefully this makes sense intuitively, right? If you think about what the derivative is, it's the change in the derivative of a function of x is the change in x with respect to, is the change in the function with respect to x, right? In this case, the velocity conceptually is the change in position with respect to time. Okay, so the derivative of the position function here with respect to time. And acceleration is the change in the velocity with respect to time. Right, so that's why you see a of t being the derivative of the velocity function. Okay, now hopefully these steps here should make sense. These are very intuitive. Now, it isn't totally obvious why the second derivative of the position vector is equal to acceleration, except insofar as it produces velocity, and velocity produces acceleration. Okay, so this is the big idea that we want to explore here, right? The relationship between position, velocity, and acceleration. Okay, and so yeah, of course, recall that velocity and acceleration are quantities with direction and magnitude. So they're rightly modeled as vectors, appropriately modeled as vectors. With magnitude and direction. Okay, that's the key to a quantity being appropriately represented by a vector. Okay, so velocity and acceleration. Right, when we talk about the velocity, we're talking about the velocity of a particle. You know, it's going to have a certain speed, which would be kind of like the length of the vector, and it's going to have a definite direction. The velocity is in a direction. Same with acceleration. Okay, so they're vectors. Okay, let's formally define this thing here, and then we can move on to some examples and flesh this out in a little more detail. So if x and y are twice differentiable functions of t, okay, just basically what we saw above, x is a function of t, y is a function of t, and they both have the second derivative exists for both, and r is a vector valued function given by r of t equals x of t times I plus y of t times j, then the velocity vector acceleration vector and the speed at time t is, okay, so all of these things, so the velocity, we call that v of t, vector value function of t, it's equal to the derivative of the position vector. And we know how to differentiate those vector valued functions from the previous session, so we know that that's just x prime of t times I plus y prime of t times j. Okay, and acceleration, that's a of t. Okay, that's going to be the second derivative of position, and so accordingly it'll be the second derivative of the x component and the second derivative of the y component, the j component. And so there's your velocity vector and your acceleration vector as derived from position. And then finally speed. Speed is sort of basically speed is going to be the magnitude of the velocity. So if once you kind of get rid of the direction piece of the velocity vector, what you're left with is speed. And so it is quite literally the norm of the velocity vector. Okay, which is obviously the norm of the derivative of the position vector. Okay, we know how to calculate that. It's going to be x prime of t, you're going to square that, and then it's going to be y prime of t, and we'll square that as well, and take the square root. All right, so there we go. So that is velocity and acceleration. Okay, so that's kind of the definition here. Now, if you take physics, this will be probably like first week you'll get into this right away, and so this will sort of taken, well, I think it's described pretty thoroughly usually in most introductory physics courses, but they may put it in slightly different terms. Vector valued functions may not be the terminology that is used. That's a more general expression of this than what you might get in introductory physics. Okay, let's do an example. Okay, let's do an example. Let's find the velocity velocity vector, the speed and acceleration vector of a particle that moves along the plane curve we'll call the plane curve C, described by, and here's our position function. It's going to be r of t equals 2 times the sine of t over 2 times I plus 2 times the cosine of t over 2 times j. Okay, so we've got some position function, and what we want to do is identify the velocity and acceleration functions for this guy, and we also want to know the speed, okay, at time t. Okay, so it's pretty straightforward. The velocity vector can be identified as just the derivative of this, right? Okay, so we would need to differentiate both of the components here. Okay, we can do that. And so what do we get here? Well, this would be the chain rule from Calc 1, recall. So this would be 1/2 times 2, and now instead of sine, it'll be cosine of t over 2 times I plus, and then the same kind of thing here, 1/2 times 2, actually it'd be negative, won't it? Well, we'll put the negative inside. Negative sine of t over 2 times j. And then we can do some cancellation here. So this would be cos t over 2 times I, and then minus sine of t over 2 times j. Okay, no problem. Okay, so that's the velocity vector. Okay, so that's part 1. So we got that piece. All right. How about the speed? We can quickly get the speed out of this, right? The speed is going to be just the norm of this vector. Okay, so the speed is the norm of the velocity vector. Okay, and so that's going to be just basically square the components and add them together. So it'll be cos squared times, or cos squared of t over 2 plus sine squared of t over 2. Technically that's negative sine squared, but then when you square it, of course, it becomes positive. And then the square root of that. And so we know that this would be just 1, isn't it? Right, so the speed is 1. And so what you can see here is that in this particular example, the speed is constant. Right, so normally this would, I guess you'd want to think of this as a function of t, right? The speed could presumably change at various values of t, but in this case there is no t, right? The t's kind of disappear in the expression because of the Pythagorean identity that's coming into play here. So the speed here is constant. So this is this particle that's moving has a constant speed. Its velocity is not constant, but its speed is, right? So its speed is always the same, but its direction may be changing. Okay. All right. What about the acceleration? All right, so the acceleration, well, that's the second derivative of position, also known as the first derivative of velocity. All right, so we just have to differentiate this guy right here. So that is d dt of cos t over 2 times I minus d dt of sine of t over 2 times j. All right, and so this again would be a negative 1/2 times the sine of t over 2 times I. And then over here it's minus, and then this would just be 1/2 cos, right? Yep. Okay, so that is what the acceleration looks like. Okay, so now we have the acceleration as well. All right, so we technically have all of the things that we need. So we've got the velocity, the speed, and the acceleration here. Okay, now notice the velocity and acceleration vary for every value of t. Speed is constant. Okay, so that's all fine and dandy, but what is actually happening here? Like what is this particle actually doing? Let's kind of explore this example a little bit deeper. See what else we can see here. Okay, so what does the path of a particle look like in particular? Start with that. What does the path of a particle look like? Okay, so there's a couple ways to do this, of course. We can pretty quickly just use like parametric equations and some trig to get a nice feel for what this expression looks like, or sorry, what the path of this particle looks like. So we know that x as a function of t would be 2 sine of t over 2, right? Just pulling that straight off of the position function. And y as a function of t would be 2 cos t over 2. Right, again, just pulling that right off of the position vectors. And we know then that we also know that, you know, when you add these two together, well, we know that, sorry, sine squared of x plus cos squared of x equals 1, right? We know that part, right? So we can kind of use that fact in conjunction with these two to basically crank out a nice, like, regular Cartesian equation, right? So what we can do is we can take this guy and we could say, well, sine of t over 2 is equal to x over 2, and cosine of t over 2 is equal to y over 2, right? Just kind of taking these two and, you know, basically dividing both sides by 2. Okay, and one second here. And given that fact, we know that sine squared of t over 2 plus cos squared t over 2 equals 1. And so that's going to imply that this squared plus that squared is equal to 1. Okay, which obviously implies that x squared plus y squared equals 2 squared, and this is the equation of a circle, okay, with radius 2. Okay, so that's going to be the path of the particle. The particle is basically going to be a circle. Okay, so let's try to draw something here. It's pretty easy to draw a circle. Easy to draw a circle, but not easy to draw a great circle. We don't need a great circle. We just need a picture to look at here. Okay, so that is the path of our particle. Now, we know that vector-valued functions, and specifically this position function that we're interested in right now, is going to have an orientation, meaning that as t increases, the vector-valued function is going to have a definite direction that it moves around this circle. Right, so let's see what that might be. So when t equals 0, what do we get here? That means r of 0, right? If I plug 0 into the position function, I am going to have, this will be like 2 times the sine of 0, I plus 2 times cos 0, j. Okay. Right, and 2 times the sine of 0 is 1, right? Oh, sorry, that's 0. Sorry, this one is 0. So this would be 2 times 0 times I plus, and then and then cosine of 0 is 1. and that'll be 2 times 1 plus j, right? And so at time t equals 0, the position is 0I plus 2j. Well, so that means it starts here. Now, what happens when we start moving, right? When t starts ratcheting up? Well, because we're dealing with sine functions, let's go ahead and plug in t equals pi next. Right, obviously 0 to pi, kind of making a jump there, but because this is trig, these are trig functions, you get nice values when you plug in things like pi. So when t is equal to pi, then we get the position function, r of pi, would be equal to 2 times sine of pi over 2 times I plus 2 times cosine of pi over 2 times j. And what do we get here? Well, sine of pi over 2 is 1, right? So this one is 1 here. And this one is 0, right? So this would be 2 times 0 times j. So that means this guy here is going to be 2I plus 0j at r equals pi. Okay, and so that means what? Where's the particle going to be when t is equal to pi? Oh, shoot, I did it just exactly backwards. So this one was supposed to be 0, 2. Sorry, this is t equals 0 up here. Sorry. So the first one is up here, t equals 0 is here, and this is t equals pi. Okay, right? And so obviously the particle is moving in this direction, isn't it? Yeah. So there's an orientation here, and it's going to be a clockwise orientation. Right, and you could plug in a few more values to see exactly what that looks like. Maybe the next value to plug in would be 2 pi, and I bet you get something down here. Right, and then if you plug in 3 pi, you would probably get this guy over here, right? Okay, so the orientation of the position vector function is clockwise in a circle, obviously. Okay. All right. Okay, so this gives us some additional insight here, right? So we can specifically see, what the position function is doing, right? We can see that it basically is moving in a circle. Now we saw that velocity was non-constant, and we saw that acceleration was also non-constant, but that speed is constant. And so what we can say from that is that the particle is going to move around this circle in a uniform way, right? It's going to appear uniform. The speed will not vary, right? And so that's why I'm confident that if you plug in 3 pi or 2 pi, it'll be here. If you plug in another pi, 3 pi, it'll be here. 4 pi, it'll be back to there, right? So it'll always, it looks like it'll move around the circle in a uniform way. Now, what happens with velocity and acceleration as t is changing? Okay, so this is a little bit more complex, but we can definitely look at this. So let's say can we see where the particle is going over time, and have the vector valued function, and how these vector value functions work together. Okay, so we know what the path looks like, but let's see what happens with velocity as time changes, and also with acceleration. So we're going to start just level setting here. Let's level set, and I'm going to switch notation. We're going to switch to the vector notation here. So this will be 2 sine of t over 2, comma 2 cos t over 2. And the reason I'm switching here is because we're going to build a table. of values. And it's just a little easier when you've got the component form like this, I think. So this will be cos of t over 2 and negative sine of t over 2. It's also useful being able to switch between these two notations. Sometimes you'll find that students will get like really like fixated on a particular notation to the exclusion of another, and that's not ideal because these notations have strengths and weaknesses, right? So sometimes this is better than the other, and vice versa. And so this was negative 1/2 sine of t over 2 and negative 1/2 cos of t over 2 for the acceleration. Okay, so we've got these three. All right, and so what we're going to do is we're going to build a table. Okay, and so we'll have a t that we'll plug in over here, and we're just going to plug in 0, 1, 2, and 3, okay, for our t. Okay, and then the argument of our functions are all t over 2, so we're going to have another column here where we basically divide t by 2. Okay, so this would be 0 again, this will be 1/2, this will be 1, this will be 3/2. Okay, so plugging in these kind of uniform t's and dividing everything by 2. Okay, and then we're going to evaluate r of t, v of t, and a of t at each of these. Okay, now we'll do the first. We'll do this for 0 just to make sure we can see how this is done, but then I did this separately using Excel, Microsoft Excel, just to make it quicker because it can get a little tedious. But if we plug in 0 for r of t, then it's 2 times sine of 0, right? And so we already saw that that's 0. And it's 2 times cosine of 0, and we saw that that was 2 times 1, so that was 2. Okay, so we get 0, 2 for the position at time equals 0, which we already saw. What about the velocity? Right, what happens when we plug in 0 into the velocity vector? Well, it's cosine of 0, basically, right? So cosine of 0 is 1. What happens when we plug in 0 to negative sine? Well, we get a 0. Okay, and then what about for acceleration, the acceleration vector here? When we plug in a 0 there, we get negative 1/2 times the sine of 0, and of course that's going to be 0, and then we get negative 1/2 times the cosine of 0, so that's negative 1/2 times 1, and so that is just negative 1/2, and I'm going to write these as decimals because they're not going to be nice as soon as we move past this line. Okay, all right, and then I'm just going to backfill some of this so we can get some values. Right, and so when we plug in 1, we get 0.5, comma 1.94, and these are approximations, obviously. And then for velocity, we get 0.97, comma negative 0.25. Then we get negative 0.12, comma negative 0.48. Okay, so that's what it looks like at t equals 1. And at t equals 2, 0.96, comma 1.76, and then 0.88, comma negative 0.48, and then the acceleration at time equals 2 is negative 0.24, comma negative 0.44. Okay, and then at time equals 3, the position is changed again to 1.36, comma 1.46, and then 0.73, comma negative 0.68, and then finally the last one is negative 0.34, comma negative 0.37. Okay, so obviously a lot of movement here, right, as we would expect. But can we make some sense of this? Can we make some sense of this? Well, I'm going to draw what each of these looks like. So what does t equals 0 look like? Okay, so the position vector is at 0, 2, so I'm just going to denote that as 0. Okay, so this will be kind of 0, 0. All right, imagine the plane here. And so the position vector is at 0, 2, so we'll go up 2, and that's RT. Well, R of 0, sorry. Okay. And what is velocity doing then? Well, it's 1, 0. So it's going like this. Okay. And how about acceleration? Well, acceleration is 0, comma, negative 0.5. Right, so 0, comma, negative 0.5 looks like that. Right? And so that's what's happening at time t equals 0. Position is here. Remember, this is on a circle. Right? But the position is up at the top. We saw this in the previous little bit we were working on. What happens at t equals 1? Right, this is where it starts to get interesting, when we start to move. Okay, so at t equals 1, the position vector has obviously changed. So now it's 0.5, comma, 1.94. Right, so let's put some values. That's 1, and that's 2. Right, so it's a little bit off. It's up right about here, we'll say. So it's a little bit off of where it was last time. Right, so that's R of 1. And what about the velocity? Velocity is 0.97. Okay, so it would be over just about 1, and then down about a quarter. So it's like right about there, we'll say. Okay, and so that's the velocity at time equals 1. And the acceleration is negative 0.12, comma, negative 0.48. And so what you'd find is that that one is parallel to the position vector. So it looks like that. And I'll do the other two a little bit quicker, but you can verify this. Right, so when we get to time equals 2, we can see that it's 0.96, 1.76. So it's just a little bit further over. So something kind of like that. Right, and then what we'll find is that the velocity is doing that, and the acceleration is doing that. Right, so you've got this kind of triad here. So, and then, well, just for completion, we'll put in t equals 3. Since we have the data, it's just a little bit further over, isn't it? Right, it's 1.36 and 1.46. So it's a little bit more than that, and then, let's see, 1.46. So it's something kind of, it's maybe over here like this, we'll say. Right, and velocity is doing that, and acceleration is doing that. Okay, and so for each of these, you can kind of see that as time starts moving, the position is changing. It's obviously going to go in a circle here. Right, so it's just getting further down on the circle. Okay, so it's just moving along the circle. Velocity is always perpendicular. Right, you can see that's a right angle, and for each of these, velocity is always perpendicular to the position vector. And acceleration is always perpendicular to the velocity. Okay, so very interesting. So this is one way to draw it. Another way to draw it is to kind of take this and sort of move the vectors around a little so that they're a little easier to interpret. Okay, so another way to draw it would be to kind of put them all on the same plot. Okay, so let's draw this a little bit larger. Okay, and so we'll make 1, 2. Okay, so at the start, your vector is here, your position vector. Okay, and your velocity is going like this. Okay, and then your acceleration is some direction. You know, if the particle is here, it's basically pointing towards the center of the circle. Okay, this would be t equals 0. Now at t equals 1, it's moved off a ways, off of the axis there, right? But again, your velocity is perpendicular, and your acceleration is towards the center of the circle. This would be t equals 1. And then further, This would be t equals 2, right? So your position is always the vector extending from the center of the circle to the perimeter. Okay, that's your position. Velocity is always perpendicular to the position, and acceleration in this case is parallel to the position, but obviously pointing towards the center of the circle. So the acceleration is always towards the center of the circle. Okay. All right, so we can see that the velocity vector is always at a right angle to the position vector, and the acceleration vector is always at a right angle to the velocity vector. And it's always pointing that, what that implies is that it's always pointed towards the center of the circle. Okay. So we can see that the particle moves clockwise at a constant speed because the acceleration is always orthogonal to the velocity, right? The actual speed remains constant, right? So the velocity is always, the velocity and acceleration are always orthogonal to one another. So that's what keeps the particle from accelerating or decelerating, if you want to think about it like that. Okay. Very cool. Okay. So very cool. And you can imagine this is the circle, and it's just going to continue doing this all the way around the circle. Okay. Very cool. Okay. Let's do another example. Kind of a shorter one. That one we went a little bit deeper on just because we want to kind of flush some of this out. So let's take another example. Let's sketch the path of an object moving along the plane curve given by, here's the position vector, so it's RT equals t squared minus 4 times the I vector plus t times the j vector. Okay, so we want to sketch the path of this object, and we want to find the velocity and acceleration. And let's specifically find the velocity and acceleration when t equals 0 and 2. All right, so 2 specific times. Okay, so we can sketch the curve pretty easily, right? So we can notice here that x of t is t squared minus 4, and the y of t is just t, right? And so we can combine these two, and we see that x will be equal to y squared minus 4, right? Just basically you got a t here, t equals y, so plug the y in over here. Okay, so you've got this guy here, and so this is going to be basically like a parabola, except, you know, x is a function of y here, so it kind of is going in the direction that we're not used to, but we can draw it very easily. It kind of looks like this. Okay, so this is the y-axis and the x-axis. Okay, so that's basically the sketch, right? Now there's an orientation to this thing. Okay, so let's kind of flush some of that out. So what's the velocity vector going to be? We'll need that and acceleration here. We're trying to find that. We'll get to the orientation in a second. Let's do this first. So this is r prime of t, right? And so that's going to be just the derivative here would be 2t times I, and then the derivative here is just j, basically. So there's your velocity vector. The acceleration vector is going to be the derivative of velocity, and so it's just going to be 2i, isn't it? Right, so 2t would differentiate down to 2, and then just 1 becomes 0. Okay, so here's your acceleration vector. And so we could very easily figure out what this is doing at t equals 0. Well, you've got v of 0 and a of 0. V of 0 is going to be 2 times 0 plus 1, right? So it'll be just 0, comma, and then basically 1, right? And then the acceleration at 0 is just going to be 2. It's constant again. Okay. And then t equals, what was the other one that we needed? T equals 2? Yep. Velocity at time 2 is equal to 2 times 2, so 4, 1. And the acceleration at t time equals 2 is, again, constant, 2, 0. So you can see that the acceleration is constant here, right? Because the vector equation is just a constant value, 2 times I. Right? So it's the acceleration here is constant. What does that mean exactly in the context of a path like this? Well, let's take a look at another drawing here. Let's say we have, right, so the path looks like this. We saw 1, 2, 3, 4, 5, and 1, 2, 1, 2. So we know that it cuts through here. It kind of goes up like this, and then it does one of these, right? Well, so A of 0 is 2, 0, and V of 0 is 0, 1. Right, pulling that from the previous page. And so the velocity at t equals 0 is like this. And the acceleration is, well, I mean, it's 2, 0, right? So you're drawing it, from the center of mass of the particle, it would look like this. Okay. And what about at t equals 2? Sorry, t equals 1. Let's do t equals 1. So acceleration at time equals 1 is, again, 2, 0, and the velocity is 4, 1. Sorry, it's, 4, 1. Sorry, that's t equals 2. Sorry, we just did those. So at t equals 2, the velocity is 4, 1, right? And the position is here, right? And the velocity is going to be 4, 1, so that's like 4 and 1, right? So you can think 1, 2, 3, 4, and 1. So it's kind of doing this. And what's the acceleration doing? Well, it's like this again. It's still the same. Right? Now notice that the velocity here has a larger magnitude at time equals 2, right? That's because the acceleration is in the direction of the velocity. Right? So the particle is speeding up. Right? It's the magnitude of the velocity is increasing. Whenever the acceleration is in the direction of the velocity, then that's going to increase the velocity. That's the nature of acceleration, right? Here you can see this is where it's going to be the slowest, and then it's going to start to, well, yeah, it'll be the slowest here, and then it'll start to pick up. Okay. Very good. Very cool. Okay, another example, and then we'll shift gears a little bit here. Another example. All right, so an object starts from rest at the point P, and this will be a three-dimensional point, so 1, 2, 0, okay, and moves with an acceleration of, and here's the acceleration function, it's going to be equal to j plus 2k. So constant acceleration, where we're given the norm of a, is measured in feet per second squared. Okay, so the magnitude of the acceleration is in feet per second squared. So we want to find the location of the object after t equals 2 seconds. Okay, all right, so this is kind of a reverse type of example, right? In this example, we're told where the point starts, and we're told how it accelerates from that starting position. So remember, the acceleration is going to have a direction, and it's going to have a magnitude, right? So we're told where it starts, and we're told in what direction it starts to accelerate and what that acceleration looks like. And so the question here is, where is this thing to be found after 2 seconds? Okay, and so we're given acceleration, we're asked to find a position. So that means we're going to have to reverse the process. We have to use acceleration to derive position. Okay, so what that means is we're going to be integrating a vector valued function to get another vector valued function. We're going to integrate acceleration to get velocity, and then we're going to integrate velocity to get position. Okay, and so a couple of things that we can pull out of here that are important first. So important to note, right, from the problem, things that we'll need. Right, the object starts at rest, so that tells us that the velocity is at 0 is equal to 0. Right, it's kind of like a condition, an initial condition. Okay, so the object starts at rest, so the initial velocity is 0. Further, we're told where it starts. I'll put why this is true. So velocity at 0 is equal to 0 because the object starts at rest. Okay, that's kind of the reason. And then we also know that we know the position at time 0. Right, we're told that. Right, specifically that's going to be some vector valued function evaluated at 0, at t equals 0. But we know what it needs to look like. It needs to look like this. It's going to be 1i plus 2j plus 0k, right? How do we know that? Because the object starts at p, and we're given that point, right? 1, 2, 0. Okay, so these are two things that we know. Okay, and so we can use these facts to kind of get back to our position, the appropriate position function. And this is really important because when you integrate, remember there's that integration constant, and we're going to need these initial conditions to push through the integration constant piece of it. Okay, so let's find the velocity. V of t, that's going to be equal to the integral of a of t. Okay, we're going to integrate the acceleration function. And so you can use whatever notation you prefer, but I am going to use this one. Let's see here, one second. I lost my spot. This would be 1, 2, 0. Okay. Oh, sorry. Nope, I'm sorry, I wrote that wrong. The acceleration function is here. The acceleration function is 0, 1, 2. Right? I was confusing it with the initial. So 0, 1, 2. Okay. Now, sometimes people don't like this notation. You could also write the notation like this. You could write 1 j plus 2k. Right? It's basically just a constant. It's a constant function, right? So it kind of looks like you're writing a point, but technically this is a vector value function. Okay, but I'm going to write it like this because I prefer this notation. And so can we integrate all of these pieces? Yes, we surely can. This would be 0, t, 2t. Okay, and then very importantly, plus a constant vector. Okay, and this is where the we need to figure out what this constant vector is before we can integrate velocity to get position, right? That's why we need the initial condition, right? So we know that v of 0 is equal to basically this guy, so it would be 0, 0, 2 times 0 plus c1 write it like that. And we know that that needs to equal the velocity at time 0, which was 0, 0, 0. Okay, and so what does that imply? Well, it just implies that all of the constants are really 0. So the velocity function is just this. It's just 0, comma t, comma 2t. Okay, very easy. Okay, so now what we'll do is we'll use the velocity, we'll integrate the velocity to get the position. Okay, and so r of t, the position function, is going to be equal to the integral of velocity, okay, which is what we just saw. It's going to be 0, comma t, comma 2t dt. And so this guy's really easy to integrate. This is 0, and then it's t squared over 2, and then it's 2t squared over 2, which is just t squared, and then of course plus some constant. Okay, so just basically like the previous one, now we need to use the initial position of the particle to figure out what these constants are. And so r of 0 is going to be equal to, plugging in 0 for t, you get a 0, comma 0, comma 0, plus c1, c2, c3. That needs to equal the initial position of the particle, where we're told that it is initially at 0.120. Right, it's sitting there. And so what does that mean? That means c1 is equal to 1, c2 is equal to 2, and c3 is equal to 0. Okay. Right, and so the position vector, therefore, is equal to, it's going to be this guy, 0, comma t squared over 2, comma t squared plus 1, 2, 0. Right, and you can write this in a couple different ways. And so one way to be just to do like a vector addition kind of thing here. You could just write, so instead of 0, it's 0 plus 1. Right, so you get 1 for the x component, and then the y component is t squared over 2 plus 2, and then the z component is just t squared. Right, so this would be one way to write it. So r of t equals 1 t squared over 2 plus 2 and t squared. Or, you know, if you prefer, you could write it like this. This would be I plus t squared over 2 plus 2j plus t squared times k, right? So there's the position function. Whichever way you prefer, you can write it that way. Now, what is the position of the particle at t equals 2? Well, it's easy to find at this point. Right, you just plug in a 2. So r of 2 would be 1, comma, and then this would be 4 over 2 plus 2, and then that's just 4. So 1, and then 4, and then 4. Okay, so that's the location, and so specifically at 0.144 is where the particle is at. This is the vector that describes its position, but then that's where it's actually sitting. All right, perfect. Okay, so I think we'll have to do this lecture in two sections. And so we'll end the first section here, and then we'll jump into projectile motion in part B.